Hello, I'm Courtney Carr, Director of Marketing and Education for IAPD. Thank you for joining today's e-training webinar, PAEK, Characteristics, Properties, and Applications, presented by Jason Lyons of Arkema. During the presentation, you may submit questions into the Questions tab on your webinar toolbar, and we will answer them at the conclusion of the presentation. Following the webinar, you will receive a link to a survey. Once you have completed the survey, there will be a link to download the presentation slides. You will also receive a recording of today's webinar. Feel free to share the recording and slides with others in your office. Jason Lyons is currently the Business Manager of PEKK product line with the Technical Polymers Division at Arkema. Prior to accepting this role, he was a Research and Development Manager within the Arkema Coating Resins Division, working on the optimization of the impact modifiers and process aids for various resin systems. His area of expertise includes polymer processing, impact modification theory, and polymer mechanics. Jason received his BSc in Textile Engineering from Philadelphia University and his PhD in Materials Engineering from Drexel University. To date, Jason has more than 30 publications and presentations with 5 issued patents and several others pending. I would now like to turn the presentation over to Jason.
So good afternoon and good morning, everyone. Courtney, thank you very much for the introduction. It's my honor and pleasure to be here today to talk about something that if I went back 5 years ago, I really had no knowledge of whatsoever. And so I'm going to talk about PAEK today, so the general family of polyaryl ether ketones, give everyone an idea of where they're used, how they're used, why they're used, and more importantly, the differences between them. More often than not, when I speak to someone about PEKK, they immediately come back to me and say, oh, I'm very familiar with PEKK. And so I want everyone to leave today knowing that those materials are different and the qualities of each of those. So diving right in, my intent is to keep this short today. I'm respectful that today is Good Friday, and also I want to be mindful of your time on a holiday weekend and for lunch. And so I will challenge myself to finish this in 20 minutes or less. And so considered a crash course within the high temperature thermoplastic space, hopefully leading to further discussion down the road because I will give you my contact information at the end. And so if we go on to IAPD's website, we see the famous thermoplastics rectangle. And I know this is an eye chart, and so we blow it up on the next screen. But if you look at the bottom, we're starting at commodity plastics, and that's where my life was spent. And then as you go up to the top, you're going more and more into the engineering resins and the high thermal performance plastics. And so the arrows shooting upwards are an indication of performance. They're an indication of the temperature resistance. And then unfortunately for most, they're also an indication of cost, with those on the top being extremely more expensive than those that are on the bottom. And then for today's talk, we're going to zoom in on the one that's in blue, the high performance thermoplastics. So we'll blow that up going on to the next screen. When we go into this space, there's a lot of people, particularly if you're dealing with aerospace or you're dealing with the oil and gas industry or the medical market, that are familiar with a lot of these materials. And a lot of these materials are selected in the first place, quite frankly, because nothing else works. Oftentimes when we're going into a new account and asking them about high temperature thermoplastics and they're asking me for information, very often the first question that I ask is, have you tried everything else? And the reason that I'm asking that is that if you haven't tried everything else, there's a good chance that something may succeed. And then if nothing else is succeeding, then that at least is the first barrier to entry to get over to sticker shock to that high cost that we mentioned on the last slide. And so if we look on the bottom of this slide, you'll see that there's some properties that are attributed with the semi-crystalline high temperature thermoplastics, which is that HTTP, which you'll see referenced a lot. And so typically difficult to thermoform, they're typically semi-crystalline and opaque, and they have a lot of good properties. And if I go back to that last chart, I'll notice that, and I blew it in, is that we're going to focus on these two today, PEK and PEKK. And so even going back, I'll give a little bit of jab to Courtney. So PEKK was not listed on the prior chart. And so it's an indication that there's a lot of newness to this material. And if we look at the global capacity of all polyaryl ether ketones, we're going to say that PEKK or PEKK represents less than 5% of that. And so we're really speaking of a niche when we're talking about this material. And we want to introduce you to it, give you some background to it so that you too in the future can differentiate between PEKK and PEKK. So I can, in theory, spend 20 minutes on this slide alone. It's the main drivers that the consumer has within polyaryl ether ketones. And so why are we going to this class of material? There's a lot of data that I will give you because I know that you'll have this presentation as a reference, and so we won't go into a lot of it here. But when you're looking around this, if we start with the processing options, the high temperature thermoplastics are not very different from your regular engineering materials, except that you need to go to a little bit of a higher temperature. If we're looking at PEKK, when we're talking about extrusion of PEKK, we limit our extruders at 385 degrees C. Those that are familiar with PEKK, they go a little bit higher into the 400 degrees C range. And most extruders have the capability of doing this, although some are a little hesitant to go up that high with fear of potentially breaking a shear pin or something like that. But in general, these materials are the same as you would expect from any other material. We're injection molding them, we're extruding them, we're powder coating them, we're using them in 3D printing, thermoforming, etc. And when we're thinking about what are we doing them, why are we using them? High temperature resistance is probably the most common request that I get is that I need something to last at a very, very high temperature and everything else is well over its TG or it's melting, please help. When we go into these materials, chemical resistance is out of this world. It's absolutely fantastic. The whole family of PAEK is resistant to nearly everything that you can think of. Flame smoke toxicity we'll show you some data on as well, and it's the reason that these materials are used a lot in the aerospace industry, is that they're very difficult to burn, and if they do burn, they're typically releasing things that aren't the nastiest of the nasty. Strength and toughness is implied from before, is that they're extremely tough. We'll show you some data on that. And then as we go to the left-hand side of the circle, we start to see some differentiation between these materials. And so low wear and friction. So if we're looking at that, if we're looking at tribological grades, we know that Torlon is a very, very heavily used material in that space. And when we're thinking about that, they're fantastic there. We also know that PEKK is used a lot in wear and friction, typically in bearings and bushings. And when we also can see that PEKK is also being used and identified in that space. And so we're trying to identify where it makes sense, how to use it, how do the three compare together. We go into electrical properties, and that these materials are fantastic insulators and used in the wiring cable industry as according to that. Permeability is interesting, and we won't go into detail a lot about it today, other than to say that these materials are extremely good with permeation resistance. If you're familiar with PBDF, and the polyaryl ether ketones can be anywhere from 80 to 300 times more effective in permeation resistance against things like CO2 and sour gas. And so when we're thinking about applications where that may come into play, it's a very good arena for these materials to exist. And then a lot of my presentation today is going to be focusing on this concept of tunable crystallization. The reason for that is that PEKK is a copolymer and PEKK is a homopolymer. And by the mere nature of that alone, it's going to show some different performance properties that I want to elaborate on. So I'm not going to spend a lot of time on this because I didn't want to educate you on the things that are necessarily similar with all of the materials. I wanted to spend some more time on where they're differentiated, but I stuck it in this presentation so that you would have it as a reference. When we're looking at the polyaryl ether ketone family, it's much, much easier and much shorter to list the things that actually do have an impact on them. And so the way to read this is that if there's a letter A, so if we look at MEK, at room temperature, there's no attack. At elevated temperature, we go into a slight attack, and C is a severe attack. If you see that there was a C at 23 degrees, so we had a severe attack at room temperature, we didn't yet go to the higher temperatures just because, as many of you know, these tests are very costly and timely. And so we want to make sure that we're getting as much data as we possibly can. But this is the list of things that we are typically trying to avoid. If it's not on here, it's generally regarded as safe against the materials that we're showing. And this is true against all polyaryl ether ketones. The reason that I'm showing the PEKK data is that's what I have access to. So again, Looking at this, there's not a lot that these materials can't withstand. And if it's all of these things are being present anyways, it's probably an environment that I don't want to be present in myself. Going on into FSET, so flame, smoke, and toxicity, this is very prevalent for the aerospace sector. And so we're looking at materials that are inherently flame retardant without the use of any type of additive. And so when you're looking at it, we have a V0 rating, we have limiting oxygen indexes that are 35 to 38 for PEKK. That difference is shown between the different grades that exist. Some other PAEK may go up into the 40 range, but inherently all of these materials are very, very good. One of the things that I wanted to show is that the smoke toxicity for PEKK is that when these things eventually do burn, we see a lot of non-detecteds for everything other than carbon monoxide and carbon dioxide. So it's an area of interest and one of the main reasons that the aerospace industry has taken interest in these materials, particularly on the interior of the aircraft. There's not a lot to show on this except that this data is relatively fresh. We know that there's a lot of interest in PAEK and for electrical properties. We're looking at relative permittivity data of around 2.9, and that's similar for a lot of the materials in this range. I'm showing again PEKK data as that's what I have access to. And one of the things that was recently requested of me was to see what's happening with the dielectric constant as a function of temperature. And so we did that test. We ran it at a few frequencies, and the asterisk is on the 50 hertz because I had to interpolate between 40 and 63, which we are capable of running. And the data that's in the squares or rectangles at the end is what I want us to focus on, is that there seems to be, as you get into higher temperatures, that there may be some distinct change that's happening. If we're looking at lower frequencies, 50 hertz, if we're looking at a PEKK material, we're seeing 11 and 17, and then we are seeing with PEKK, depending on, we'll talk about what these numbers mean in a couple of slides, but we are seeing a slight drop, and we have to reproduce that to see if there is anything that's going on with that. If we're thinking about the chemical structure as we know it, there may be some correlation between that, and it's something that we're diving into a little bit more deeply. I just wanted to present it here because it's something that we thought may be of interest, and so we're continuing to explore to see what realm of possibilities exist when we're speaking of electrical properties. So I'm not going to spend a lot of time on mechanical performance, but I just wanted to say that typically these things are able to meet the most demanding applications. When we're looking at these numbers from those that come from a commodity space, they're gigantic. And so 100 to 120 megapascals for tensile strength, depending on the PAEK that you're working with. Tensile moduluses are high, fluxural moduluses are high. If I put the compression modulus, it's in that same ballpark all the way up to 3.9 gigapascals. And the CUT, for those that are not familiar with this, it's continual use temperature. And so I actually put the 145 in there, and I put it in there for a reason. One of the PEKK grades that is a 60-40 copolymer that we'll talk about in a couple slides is actually an amorphous material. And as an amorphous material, it has a much, much lower continual use temperature. And the reason that I put it in there is to educate people is that when you're looking at comparison slides between different materials, it's really important to understand which material you're actually working with. Because similar to someone that's working in finance, you can make the charts sing in any which way that you want to make one material look better than the other. What I'm trying to do with this is just to give you the idea and the knowledge to be able to ask those questions when you see that data in the future. As I mentioned before, I came from a commodity space. I worked in PVC and I worked in polycarbonate for about 15 years. And so when you compare the numbers that you see up the top compared to what you see for polycarbonate, it quickly is evidence why there's a gigantic gap between where these materials can be used. And most prominently, it's coming over to this continual use temperature. And so more often than not, when I'm going into a new account, I'm trying to replace metal more so than I am trying to replace plastics. So I'm trying to replace thermosets more commonly than I'm trying to replace the traditional thermoplastics. And so that's a mindset that I want to get everyone into on the call, is that when we're thinking of these materials, we're not only competing against other thermoplastics, we're competing against a whole world of materials. I always like to put this up there because it was a shock for me the first time I saw it. And so again, coming from vinyl, and I'm looking at this, if I'm anywhere near these temperatures on the top end of the spectrum, I'm really, really nervous. But then if you're looking at PEKK, if you're looking at PEK, if you're looking at any of the variety of different PEKs that exist, is that the continual use temperature is above 250 degrees centigrade. And so most applications where a lot of other materials are melting, these materials are perfectly fine and happy and able to withstand a lot of hours in that environment, which is one of the main drivers for why they're being used in a variety of different markets that are demanding those applications. And we'll talk about a little bit those later. So if you walk away with one thing from this talk, this is hopefully the chart that you'll walk away with, is that there's a lot of different PAEK that are out there. Most everyone is familiar with PEKK. PEKK is a fantastic material. The people that have been making it have been doing so for decades. It's specified in a ton of places, and it's an extremely, extremely good material. I highly recommend it. And when we're looking at this, when you have PEKK, you have a material that has a TM and a TG. And if that suits the application that you're looking for, that's fantastic. The biggest differentiation between PEKK and PEKK is that, as I noted, PEKK is a copolymer. And we have copolymer ratios of 60-40, 70-30, 80-20, and then in theory, we can do 100-0. And what happens with that is you'll see that our melt temperature is increasing, but our TG is staying relatively constant. One of the biggest drivers that PEKK has over PEKK is for applications that can take advantage of that 20 degrees C. If your application can use that, then PEKK is a material that you want to explore. If 143 is perfectly suitable for where you're at, then there's no need to necessarily go for this, unless you potentially want to do something related to a little bit larger processing window, potentially, due to the lower melt temperature. But why we are concerned about this and having the different copolymer grades is that what we found is that these grades are succeeding in different market sectors. And so if I look at 3D printing, particularly high temperature laser sintering, where I have a bed at a temperature of 280 degrees centigrade for a couple of hours, this 60-40 grade takes forever to crystallize. And so in that environment, it's perfectly happy if the crystallization speed is matched with the bed temperature, which is going to resist any type of warping or things of that nature. If I look into a 70-30 grade, this one crystallizes a little bit more quickly, and so we've gone in mainly into composites area with that. And then if we want to go to the 80-20, this is the grade that behaves the most similarly to PEKK. And so if people are used to PEKK, they should have no problem with this material. And we talk about injection molding here, but that's also its extrusion grade. And so one of the interesting things with PEKK is that we have one chemistry, and simply by how we make things and putting the molecules together, we can make products that are amendable to different applications and product lines. While with the other PEKs, there are a lot of, you have a unique polymer system that yields one product. There are some variations to this that are being introduced. So I know a lot of the people that are in PEKK production, they also have low melt PEKK that has been introduced. They also have grades that are being now produced for additive manufacturing as well. And so I think this differentiation was something that was noted in the past, and it's something that the producers of PEKK are working to rectify and moving forward. So I wouldn't be an engineer unless I had some type of engineering-like slide in the presentation. And so I didn't know the background of those that are in attendance, so I try to keep this as simple as I can. And so when we talk about these design rules, when we talk about being able to change the copolymer ratio when I'm producing PEKK, I wanted to explain why that's important. And so typically comparing PEKK to PEKK, you'll notice that PEKK obviously has one more K than it does an E. And so that ketone is this C double bond with oxygen. So you have an R group here, an R group here, and then a C with a double bond of oxygen. That bond is stiffer than an ether bond, which is just an oxygen bond in between two R groups. And so when I'm putting in an extra K, I am making something that is inherently more stiff. And so when I'm doing that, I can impact the TM, the TG, I can impact the modulus. And so we're seeing that there's slight gains in some of your mechanical performance, particularly in compression modules and compression strength. But with those gains comes the fact that I'm taking out or removing one of these ethers that is fairly flexible, and so there's some give on the ductility aspect. And so you'll find typically that a PEKK grade is more ductile than a PEKK grade. But when I'm playing with this, if we look at, this is a thermophthal moiety, this is an isophthal moiety, and it's difficult to see from this comic that we see. But if we focus on the T, you'll notice that you have on the 1 position and on the 4 position. So if you're picturing that, it's relatively linear, and these things pack very nicely, which is leading to a higher crystallization speed when I have more of this in that, say, 80-20 rather than 70-30. If we're looking at the I ratio, it's on the 1 and on the 3. And so even though it looks linear here, in reality, it's kinked a little bit. And so when we're adding that, and you'll see it at the TDI ratio, the crystallization speed is different between the different grades that we have. And this is something that I want to spend the rest of the talk talking about, is what can we do with this variation in crystallization kinetics, and how can that help us in certain markets? So this is something that you can walk away with as well. It's basically your half-time crystallization speeds for a variety of different materials. And I'm going to focus mainly on PEKK, and I'm going to focus on PEKK and the different grades that we have. As we mentioned before, the 60-40 PEKK, this red line, takes forever to crystallize. But if I'm working in high temperature laser sintering, and I have that material in a bed for 10 hours at 285 C, then eventually it's going to get to a relative state of crystallinity. If I'm working with these grades, they're a little bit slower, and anyone familiar with working with PEKK is that it crystallizes extremely quickly. It's a material that crystallizes like lightning, and that can be good, or in some applications that may be frustrating if you're seeing some warpage or distortion. The beauty that we have in these in-between grades, so the 70-30 and 80-20, is that at temperatures that are not uncommon in the plastics industry, say 190 to 200, I have a material here that's slowly crystallizing. It's not there yet, and so it allows me to work with it. And so what I wanted to focus on are some applications where that may be interesting for some folks. So one of the things that is very new on our radar is thermoforming. And so people that had mentioned in the past said, you know what, I love PEKK. PEKK's a fantastic material, it gives me everything that I want, but it's very difficult for me to thermoform with. And so we said, well, now that we know that we can have differences in crystallization kinetics, can we work with that? And so step 1, we make some sheet. And so the sheet can be, say, I don't know, 2 millimeters, 3 millimeters is what we've had success with so far. And we put it in an oven, and that oven temperature, say around 205 degrees, 200 and so, and we keep it in there, making sure that the part that's in that oven is not crystallizing. And so if it's crystallizing, it's too late, because that would put us down here. And if you're trying to thermoform a crystallized part, you're going to have a lot of difficulty with deep draw ratios and so forth. And so after we have it there and we've got it to that temperature, step 2 is, okay, let's take it out and quickly put it on top of a mold that is at somewhere close to the crystallization temperature. And you'll see there's some gap down here, so it's not crystallizing instantaneously. We have some time, and so when we're putting it on that, we hold it there, and then 4 minutes later in this instance, where we have some backlighting to accelerate the process, we can see that we have different colors here, and we're able to see a part that I'll show you on the next slide. So a picture speaks 1,000 words. I guess a video speaks 1,000,000. I'm not going to go through this whole video, but you see we bring the sheet out, then we pull a vacuum on the sheet. We're going deep draw, and now's the waiting process. So we have this lamp here that's simply giving heat to the back of it. So we're trying to go to that 250 degrees centigrade space. And if you have a male-female mold, you can do the same exact thing without using a heat lamp. We're just restricted by what's in our laboratories. And if we fast forward, you'll start to see that this is happening, fast forwarding, all of a sudden you're getting crystallization. And when we pop it out, here you go, you have what my daughter calls a little clown hat that she likes to play with. And what's important about this is that this is the amorphous sheet that was able to be made. And so using a 70-30 ratio, I mentioned before that we can control that crystallization speed. So it's theoretically possible, and we've demonstrated it, that we can extrude a sheet that remains amorphous. So it's not there yet. It's still an amorphous sheet. And so we can then take that and heat it up and pop out one of these clown hats. And I just showed some DSC here showing that, hey, this doesn't have a crystallization peak, has a melting peak. But if we're looking at the amorphous and we do a DSC on it, we really show that that crystallization peak pops in there prior to it. And so what we're able to see here is that through wide angle X-ray diffraction, that middle part is about 30 degrees, about 20% crystallinity, 29% crystallinity is where we're achieving, which is common with the polyaryl ether ketone product lines. So just something interesting that we're working on and trying to identify potential uses for taking advantage of the different crystallization kinetics. And the other one that I wanted to talk about is 3D printing. And so FDM, fused deposition modeling, or FFF, fused filament fabrication, is extremely popular right now. And the materials that are used a lot are basically commodities. You have ABS and PLA, and they're amorphous materials. And why is that? Is that you deposit one layer, so picture your hot glue gun coming across, and then it comes back and it applies another layer. But you're able to get some polymer chain diffusion. And so if we're looking at the interface, you have chains that are going down, chains that are coming up. And so as a result, we have good adhesion. And that's all well and good, but these materials are definitely not the materials that we want to go into aerospace with necessarily, or into the oil and gas industry, where we're exposed to a lot of chemicals, a lot of heat, etc. And so what can we do? If I go back to Formnext or Rapid or AMUG about 3 years ago, all of the talk was about printers that were able to print PEKK. And when they were printing it, and you'll notice that there's a lot of IP that exists that's related to having to do it in an elevated temperature or an oven. And the reason for doing that is that so they can try to get this interface to work. But if I am depositing this layer with a material that is crystallizing extremely rapidly, by the time I come back for layer number 2, the crystallization is already happening, and that layer-to-layer adhesion, it's simply not working unless you have some tricks of the trade that you can work with. And if you can even do that, it's still not user-friendly to work with. It can be done, but it's definitely something that's a little bit aggravating. And so if we look at this, typically we have bad adhesion amongst that. And so if I'm making other polyaryl ether ketones in a machine that I can go and buy for a couple $1,000s off the shelf, and I try to make these parts, the Z strength, so the one that's going perpendicular to the build axis, is going to be extremely, extremely poor. So we have better materials, they're more chemically resistant, they're more thermically resistant, but that Z strength is still something that needs to be focused on and needs to really, really be worked on in order to make sure that we're making parts that are suitable. And so although it can be done, is there an easier way to do it? And so what we then looked at was, with the same 70-30 ratio PEKK, is that, okay, let's deposit a layer, let's deposit a second layer, but it's not crystallizing it. Remember, it takes a long time. And so because it's not crystallizing it, it allows that polymer chain diffusion to happen. And then after that happens, then we have some crystallization occurring, which is what we're calling translayer crystallization. And this is really giving us the best of the both worlds. So taking advantage of that crystallization rate allows for better layer cohesion. That better layer cohesion shows an advantage in the Z direction without really having to struggle. And the people that are using PEKK and FFF are saying that it prints as easy as PLA or ABS, which is something that's exciting for us. And we're seeing where that goes with this whole realm of family. That was the last example that I wanted to teach you with related to the crystallization kinetics, and I'm mindful of my time and I'm already over, and I apologize for that. But before leaving, I wanted to really focus just to give you a snapshot of where these things are used. And so unidirectional tape is something that's a huge application for polyaryl ether ketones. There's also a huge application in sheet and film. Stock shape is something that is a huge market, and it will continue to be. And we have compression molding, we have extrusion of pipe, traditional injection molding as well, and powder coating. So trying to just to put these images in your mind of, okay, I'm thinking of an application, where can it potentially go? These are the most popular conversion technologies. And what I'm going to finish with is kind of give everyone a very, very brief overview of the markets that have been the early adopters. And so aerospace is by far number one. And as I mentioned before, it's related to metal and thermoset replacement. The figure that is thrown around in the aerospace industry is that for every pound that is taken out of an aircraft, it's $1,000 per pound per year per plane of savings. And so if I'm looking at a wide body where I have potentially 300 seats that are there, and if I can take out a pound from each seat by replacing the armrest from whatever metal they're using to a polyaryl ether ketone, and in doing that, so that's 300 pounds I've taken out just in the seats. So that's $300,000 per plane per year, and so the average lifespan of an airplane is 30 years. And if we're looking at the fleets flying over North America, you're looking at like 10,000 airplanes. So there's a ton of money that's there. Oil and gas, mainly offshore, is looking at being able to, if we look at pipe is heavy, and if we're going down deep, we have potential issues with that. And so can we take advantage of the lightweighting, knowing the environments that we're going into related to chemicals that are going to be exposed to, and also being very, very accurate in the temperatures that are being exposed to it as well. So oil and gas is right there along. If we go into tribological applications, if we're looking at an automotive car, there was a recent article that was out there that says there's 9 grams of PEKK on nearly every automobile. And so that's mainly just going to be found in seals and bearings and whatnot as part of the ABS system or part of the drivetrain. But there's a lot of growing opportunity in that space as well. And then on the bottom, we have smaller players, but wire and cable, as we discussed before. Consumer electronics is being driven by the fact that miniaturization is happening. And as miniaturization happens within our phones, for instance, you'll see that it gets hotter. And as it gets hotter, we need to be able to maintain all the electrical properties that we're used to. And so we need to be able to focus on high temperature without seeing any change in dissipation factors. And semiconductors are there as well. And so with that, that's my 26-minute or so crash course into polyaryl ether ketones. I know that in that short period of time, I can't go into nearly the detail I wanted to, but I hope I've given you enough information to be able to ask sensible questions the next time that you're speaking with someone in this space. And with that, I wanted to give everyone my contact information. I'm an extrovert to a fault, and I like having conversations and being abused for information. So please don't be shy in utilizing this information. And with that, I will thank you and finish up. And Courtney, if there's any questions, I'd be happy to take them.
Thank you, Jason. As a reminder, please submit any questions using your webinar toolbar. We'll give you a minute or so, and while you are typing, I would like to remind you that you will receive a survey about today's presentation. Once you complete the survey, there will be a link to download the presentation slides. In a separate email, you will also receive a recording of today's presentation. Also, please mark your calendars for Monday, May 6th for Designing Thermoplastics Fluid Handling. All right, looks like we have a question. What ratio of PEKK is optimal for stock sheet extrusion with rods or sheets?
The grade that's being used the most is the 80-20 grade. There are, and that's what's being used commercially today. It's the closest to PEKK, and that's where people have started with it. There are some people starting to explore the idea of taking advantage of the slow crystallization kinetics of the 70-30 grade, and basically trying to extrude something that is amorphous, and then post-crystallizing it later so that they can continue to process it very, very easily and then do post-crystallization at a later point in time. Depending on the thickness of the rod that you're extruding, just the latent heat inside of the part will lead to some crystallization of a 70-30 grade. And so there's a lot of work being done to say, is that bad, is that good? But if we're talking about trying to put it through your extruder today and make rod, it would be the 80-20 grade would be the one that would be recommended. And it's something that I didn't elaborate on it because I didn't want to go into too many details. But if we're looking at particular PEKK, you have the 80-20, 70-30, 60-40 is the copolymer ratio, within each of those individual grades, you have variations in molecular weight as well. And so when we're thinking about extrusion, we would choose the 80-20 that has a very, very high molecular weight, would give you the best of both worlds.
Jason, do you have a specific example where you have used PEKK and moved to PEKK?
So Arkema is not a producer of PEKK, so I do not have a specific example of my own, but I can tell you that the space where there's a lot of interest is particularly within 3D printing is the earliest one so far. One moment, please. Someone's trying to break into my hotel room. Okay, I'm back. Sorry, I requested late checkout and then they knocked on my door anyways. So if we think about applications on where people have been successful, the main one has been in additive manufacturing so far. Now what people are looking at, because quite frankly, there wasn't enough PEKK in the world in the past to make any serious considerations into re-evaluating any types of market segments. And as I mentioned before, PEKK is a fantastic material. If PEKK is working in your application, there's no desire, there's no need for anyone to go and look at PEKK. One of the things that would be interesting for everyone, though, is that if PEKK was borderline in success, perhaps in terms of taking advantage of the additional glass transition temperature benefit that you can get, or if there's something that's related to the enhanced permeation resistance to CO2 and H2S, which I did not discuss in the phone call, or if it's related to a 20% degree improvement or 20% improvement in compression strength. If those things are potentially of interest, then it can be something that, okay, well, maybe I can revisit that. If we look at the tribological grades, typically if people were unable to use a PEKK component, they would go strictly and go right over to PAI, and they would start working with Torlon. And Torlon is a fantastic material, but it may be overkill for that space. If we look at Torlon, Torlon obviously has extremely high temperature resistance, but due to its amorphous nature, it may be susceptible to chemical attack. But then when you have PEKK, that can't go as high in temperature, but it can withstand anything that you throw at it in terms of the chemical attacks. Perhaps there's some space in between for PEKK there where we can take advantage of a little bit more higher temperature that breaks into that Torlon space and also gives you the chemical resistance as well.
Great. In case someone wanted to test the properties of PEKK on a lab scale, which solvent would you recommend that can dissolve PEKK?
That's a tricky one. So due to its chemical nature, dissolving PEKK is extremely difficult to do. We have been successful and able to dissolve it into a solvent, but the solid content that you get is single digits. And so it's not something that I would recommend commercially doing, although there are several people that are looking at it. In terms of the solvent, what we use is a proprietary gamish, and so I'm more than willing to share that with you offline if there was serious interest in pursuing that pathway.
And the next question, do you have any experience related to electrospinning of PAEKs? If so, will you please share your experience, if it's feasible to prepare in nanofibers or not?
So you must have read my dissertation, because that's what I did my dissertation on, was electrospinning of materials. And so it goes back to the concept of being able to put it in solvent. And so we can put it in a solvent, but the solid content of that solution is not that high. And so we have not personally tried to do electrospinning on it, but I'm assuming that we would be able to do it simply knowing that it could be put into a solution. It would just be something that we would need to have well isolated, because the chemicals that are used in order to put these types of material in solution are not the most user-friendly things in the world. And so you would definitely be well protected if you wanted to go in that realm. In terms of fiber production, fibers can be produced from polyaryl ether ketone. There's a lot of work being done in that area, but we're not down to the nano size yet. We're probably, speaking in my textile background, we're probably in the realm of, I don't know, like 30 denier or something like that is what's achievable today commercially.
All right, thank you, Jason. That wraps up all the questions. Thank you for your presentation. Thank you for those who participated by watching the webinar and submitting questions. Please remember the May 6th webinar, and we will see you at the next one. Have a great rest of your day.
Thanks, everyone.